Okay, welcome back for segment 2. So this one I'm going to go through just a whole bunch of examples on the 3 methods that we've been talking about. Let's remember what they were. We started with linear first-order equations and did the integrating factor. Then we looked at separable first-order equations, and then we did second-order linear equations with constant coefficients. So I'll give examples of all of those. So to begin with, let's treat this one. Oops, my X is not very nice there. Now, this is a first-order equation and it's linear. So it's one of these that you would like to use the integrating factor on. So let's remember what the integrating factor is. So I'm just going to summarize the recipe over here. So this is the recipe. So we have y primed plus py is q. These are known functions of x. I need an integrating factor, which I get from exponentiating the integral of p dx. Having calculated that, I then write the solution as some arbitrary constant divided by I plus 1 over I times the integral of qi dx. Right, that's the recipe. Right, so you have to do these 2 integrals given the p and the q. Right, and let's solve this subject to y of 0 is equal to 0, and that's going to force us to pick that arbitrary constant there. So before we dive in, let's make some preliminary observations. So we've got this awkward square root there, and to make sure that that makes sense, we obviously need 1 minus x squared to be positive. Right, so we're going to be thinking about 1 minus x squared to be positive. Fine, and you know, x is 0, that's certainly within the range where that's true. So far, so good. Now, the other thing that's probably worth bearing in mind is that I need to first of all massage this equation into that form, so I need to divide by that coefficient, and then it starts to look pretty ugly. The p function and the q function start to look pretty ugly. Now, unless you had a real hard ass for your instructor, that complication of the p and the q, it can't be real. It still ought to be able, you still ought to be able to somehow do these integrals to get a fairly nice result. So bear that in mind. If you, as you're going through this, it starts to get ugly, ugly, and ugly, you may have made a mistake, so just quickly go back and make sure you didn't make a mistake, because these integrals ought to be doable. Always worthwhile keeping that in mind. Right, so let's now do the massage. Right, we want to put that in that form. So this is y primed minus x over 1 minus x squared y is equal to 1 plus x squared squared, and then I can write the square root divided by that as 1 over the square root. So my p is equal to minus x over 1 minus x squared. My integrating factor, I need to do the integral of that. And exponentiate it. Okay, so to do that integral, it's helpful to use a substitution. U is equal to x squared, so I is the exponential of the integral. Now du is equal to 2x dx, according to that substitution. So x dx is 1/2 du. I should remember the minus sign. And then there's a 1 minus u. So that's that integral, and at this point I can do that integral. You know, if you see 1 over a linear function, that integrates into a logarithm. So this is the exponential of minus, there's this 1/2 factor, times the logarithm. Now when you integrate 1 over something, in principle you should always put in an absolute value, right? integral of 1 over a linear function is the logarithm of the absolute value of it. So that's the integrating factor. Let's just go back to x. So this is the exponential of -1/2 times the logarithm of the absolute value of 1 minus x squared. All right, now, when I do this, one remembers, right, that the integrating factor had the property that it turned the left-hand side, after you multiply by it, it turned the left-hand side into the derivative of a product, allowing you to just do a simple integral to get to here. And you put the arbitrary constant in. I argued that when you calculate the integrating factor there via an integral, you don't need an arbitrary constant because any integrating factor that has the property works. Okay, so we don't have an arbitrary constant when we calculate the integrating factor, and then you might wonder about, well, do you really need that absolute value? So let's just work with it a little bit. The -1/2 here, something times a logarithm, I can rewrite as the logarithm of whatever's inside the logarithm to this power. So I can write this as the logarithm of 1 minus x squared, the absolute value, to the power -1/2. Oh, and I suddenly realized I made a mistake, because when I integrate this, there's a minus sign there, so I get a plus there. That's a plus. Okay, so that is another way of writing the integrating factor, which is convenient because the exponential of the log gives me 1. Right, it undoes the function, so I could write as 1 minus x squared, absolute value, to the 1/2. Now, back here I observed that in this equation, in order to make sense of it, I'm going to need 1 minus x squared to be positive. So, bearing that in mind, I may as well write 1 minus x squared with a square root for my integrating factor. So that's I. Okay, so we've achieved the first part of the recipe here. Let's press on. Okay, so a simple substitution inside the integral for p allowed me to do it. Bit of a rearrangement. It was looking a little bit icky around here, but by some simplifying algebraic manipulations, ultimately we got there, which is relatively simple. Okay, that's the first integral. How about the second one? So the second one is the integral of q times I. What's q? Well, q is the thing on the right there. So I need to multiply this by that and then do the integral again. Now at this stage you realize that things aren't as bad as you may have worried, because there's a 1 over the square root there in q, but when I multiply by I, I'm multiplying by the square root again. So I times q is equal to 1 plus x squared, all squared. So the integral of I times q is actually just the integral of 1. If I square that out, and then integrate, I get the following. Okay, so I have all of the pieces of information in my solution. I have that y is equal to, so it's a constant divided by I, plus this thing, also divided by I. At this stage, you see that, well, it wasn't just the differential equation that only made sense when 1 minus x squared was positive. The solution that I found, it only makes sense when 1 minus x squared is positive. So there's a limited range of validity of the solution, that function. That's sometimes what you find when you solve these types of problems. There's a domain that's defined for the solution. Okay, last piece of the puzzle at this point is to apply that initial condition to fix C. So I need y of 0 is equal to 0. So putting x is equal to 0, there I get 0 is equal to c. This whole thing vanishes, that's a 1. I get c is 0. So the solution is actually just the second term there. Like so. So that's how it all worked. Before we go on to the next example, let's just enjoy this one a little bit more. Right, so that was applying the recipe. Right, so, oh, there's these 3 steps, just do it. Finally, you apply that condition. That's how it all works. So let's just, before we leave this problem, see the integrating factor in action. So this is the problem. So what have I really done going through the recipe? So let's take the ODE and multiply by the integrating factor. So this is the ODE times I of x. So this is exactly 1 minus x squared y primed minus x. Now, when I multiply this by the square root, it's equivalent to just cancelling off a factor of the square root from the numerator and the denominator. So I get that. And then on this side, I get this. So that's what I've done. I've just rewritten that in this particular form. And the whole point is that that coefficient there is nothing more than d by dx of the square root of 1 minus x squared. So in other words, this is the square root times y primed plus the derivative of the square root times y. That's the derivative of the product. So that's just d by dx of the square root times y. And on the other side is 1 plus x squared squared. So all I've done in applying the integrating factor is to really just take the original equation, first of all rewrite it in this form, multiply by the integrating factor to get here, realize that the left-hand side is that derivative. Now I just integrate. So this bit here, you recognize is just the integral of that. That's exactly how we evaluated it. And to get this answer, it's basically just integrating that and then dividing by the square root, the integrating factor, and not forgetting the arbitrary constant of integration. So that's the integrating factor in action. That's how it works. Right? You're really just coming up with the function so that when you're here, you multiply by it and you're going to rewrite the answer. Sorry, you're going to rewrite the ODE, and in particular the left-hand side of the ODE, as a single derivative which allows you to just then integrate the problem, find the answer. Right? That's how it works. Okay. Sometimes, doing it this way, actually just realizing what you have to multiply by in order to turn the left-hand side into the derivative of a product is faster than going through that. But that's sort of a nice systematic thing to think about. Okay, so that's an example of the first method. Let's do a quick, fast clean. Looks as though I'm going to mess the board up, but as you'll see shortly, it's not quite as bad as that. Okay. Right, so the second method that we learned was one that applied to first order separable ODEs. And in some ways, conceptually, these are quite easy to deal with because you just integrate. The sort of awkwardness can come about because when you do the integrals, you end up with a function of y is equal to a function of x plus an arbitrary constant, and you get this awkward situation that you have to rearrange that at times in order to express explicitly y as a function of x. Sometimes you can't even do that. So that's a sort of a final fly in the ointment that you can encounter. Let's illustrate that and do it for a case where you get logarithms. Logarithms are sort of the instance where you need to maybe be a little bit careful because you can get absolute values in there and so forth. So it helps to think about that in a particular example. Okay, so let's do y primed equals y plus y to the minus 1 times cosine of x. Here it is, first order separable. What you do is you take the function of y here, right? It's a function of y and a function of x. That's the separable form. I divide by that. So that would be y primed over 1 plus y squared. Right, I can write this having divided by it like that. What's left over is a cosine of x. Right, so I'm following the recipe. dy dx is equal to f of x, g of y. So I divide by that. And then I integrate at a constant, and I'm just evaluating the two integrals here because by a substitution or change of variables, that's just dy over g of y. And this is f of x dx. Right, so you can think about this as a change of variable or a substitution. Sometimes you see this written slightly differently. If you were willing to chop up the dy dx, you can write this as dy over g of y is f of x dx. That's like a differential form of that ODE. And now if I just integrate it, I'm back to here. Well, there's just two ways of thinking about it. You either do it this way, keeping the derivative together and then doing a substitution, or you just treat that in some sort of a derivative form, a differential form, where you split up the dy and the dx. Either way, you get the same thing. So we're applying it to this particular problem, so I have to integrate. So I need to integrate y dy over 1 plus y squared. And I can immediately integrate a cosine into a sine and add my arbitrary constant. So this, right, there's a substitution that allows you to evaluate that. Right, u is equal to y squared, that's the substitution. du is equal to 2y dy. So I divide by 2. Y dy is 1/2 du. And then I've got 1 plus u in the bottom. So that is the same integral on the left there, which is 1/2 the logarithm of 1 plus u. And then I should put the absolute value in. Whenever you have 1 over something and you integrate it, in principle it should be the logarithm of the absolute value. So this I can write as the logarithm of 1 plus u to the 1/2 power. Taking that up there. And that's convenient because what I need to do at the end of the day is I need to remember that this equals that. So I want to undo the logarithm and ultimately solve for u, or conversely y squared. Let's just put the y squared back in. Okay, so that is the left-hand side integral. And you'll notice that it's 1 plus y squared. Y squared is always positive, so that's always positive. So actually, even though there's a logarithm of an absolute value, I really don't need the absolute value because the argument's always positive. Okay, so at this stage, I've now done all the integrals. I just need to do the final rewrite. Okay, so I've got the logarithm of 1 plus y squared to the 1/2 equals sine x plus c. I exponentiate. Having an arbitrary constant in here, which is e to the c, right, because this is just e to the c times e to the sine x. E to the c, that's just an arbitrary constant, so let's just call that something else. Let's call it a. That's another arbitrary constant, so that's what we've got so far. Now I need to square the answer. So I get 1 plus y squared equals a squared e to the 2 sine x. A is an arbitrary number, so a squared is still an arbitrary number, so in principle I could just write that as another one, e to the 2 sine x, to save this magical ink that I'm using. Okay. I'm almost at the answer. Let's take the 1 to the other side and take a square root, and then I'll be finally there. So y is equal to plus or minus, I get plus or minus from taking a square root, 1, or b, e to the 2 sine x minus 1. So there it is. Okay. So that's an application of the separable first order stuff. We press on. So we've done a couple of examples of first order things there. I'm pausing for a moment because I had this vague memory that you got a different answer to this problem. I hope I didn't make a mistake there. Okay. Let's press on with second order problems now. Second order linear constant coefficient ODEs. So let's look at y prime primed plus 9y is equal to 0 with the initial conditions y of 0 is equal to 1 and y primed of 0 is equal to 0. Okay, so this is the homogeneous problem to start with. And the recipe for this type of problem is to look at the auxiliary equation. So in general, this is the problem, and the auxiliary equation is this quadratic. Okay, so let's apply it to this. The auxiliary equation is m squared plus 9 is equal to 0. That says m squared is minus 9, so m is plus or minus 3 times I. This is this complex situation where I can write 3 different forms for the solution. So there's the complex version. And then there's the ones with simple sines and cosines. And then there's that other one where you've got a single cosine, for example. Something like that. So A1, A2, C, D, R, and delta, they're all arbitrary constants. Okay, so I'm not going to use this one. Let's just quickly have a look at the first two. It's most tempting, I think, usually to use this. So let's do that one first. So I need to calculate the C and the D given the initial conditions. So I first of all put x is equal to 0, and I get 1 is equal to C, because the cosine is 1 and the sine is 0. Then I need to differentiate. So y primed is minus 3c times the sine, plus 3d times the cosine. Now I put x is equal to 0, and I have to get 0. Sine of 0 is 0, so I get that d is equal to 0. So the solution is simply cosine of 3x. There it is, nice. So the algebra there was simple, everything was real, straightforward. Let's just have a quick look at what would have happened had I used this one. So using this form, I get a1 plus a2 is equal to 1. That's saying that when x is equal to 0, y is equal to 1. Now I need the derivative. So here's the derivative. Y primed is 3i a1 times e to the 3ix minus 3i a2 e to the minus 3ix. Putting x is equal to 0 and setting the answer to 0 gives me 0 is 3i a1 minus 3i a2. Okay. Now, at this point, I can cancel off 3i from there, and I find that a1 is equal to a2. And if a1 is equal to a2, that means they both have to equal a half. Right, so that's the algebra. So that's doing it with the exponential form of the solution, and it would work out fine. You get 1/2 e to the 3x times an I, plus 1/2 e to the minus 3ix. So that's just this other form of the solution. And in fact, it's the same as that, as you can establish by using Euler's formula. So we've got these two different forms of the solution, as either a single cosine or two of these complex exponentials. Now, had I had a slightly more complicated initial condition, let's say I had 6 there, for example, then down here, I would have had a 6, and then I wouldn't have been able to cancel off the i's, and the solution of these algebraic equations for the a1 and the a2, they would have ultimately given me complex values for a1 and a2, and so the solution here would have had these complex numbers in there. However, given that the initial conditions are both real, that would not have been a feature of solving the problem with this. I would have just got real numbers for C and D. So that illustrates the general point that usually you're given real initial conditions, and when you work with this form of the solution, you end up doing some little bit of algebra to get real numbers there and there. If you want to stick with this version, though, you'll end up with complex numbers there and have to do complex arithmetic. It's your choice. Personally, I think it's simpler to use this version. Okay, so that is an example of second order linear constant coefficient and the homogeneous problem. Let's just do another quick example. The auxiliary equation in this case was relatively straightforward. Let's just do another quick example where the auxiliary equation is slightly more complicated. So y prime primed plus 6y primed plus 9y is 0. The auxiliary equation here is m squared plus 6m plus 9. And I'm just choosing this example to illustrate one point. Now, if you throw this into the formula for the solution of a quadratic equation, you discover that you get complex roots. It's not immediately obvious how to factorize that, but you will notice that I can complete the square here. Oh, I think I've done the wrong example. Let's change the number there. Let's put 2. There we go. So completing the square there, just ignoring this for the moment, I complete the square there, it's m plus 3 squared minus 9, right? Expanding that out, the 9 cancels and I get m squared plus 6m, and now I've got the 2 there equals 0. So this is m plus 3 squared is equal to 7. Then I can take a square root. M is equal to minus 3 plus or minus the square root of 7. So at this point I realize I lied by saying that the solutions were complex. So this one, even though I couldn't immediately factorize it, I can complete a square like that, which is sometimes helpful. Now let's do a case where it genuinely is, let's put, say, 12 there. So this is now genuinely going to be complex. Here is the auxiliary equation. Now I complete the square. Right, so this piece gives me that. Now I'm going to add plus 12. Okay, so here, minus 9 plus 12 is plus 3, so when I take that to the other side, I get the following. So I get m plus 3 squared is equal to minus 3. I take a square root. I get m plus 3 is equal to plus or minus the square root of minus 3. So that's plus or minus I times root 3. And so m is equal to minus 3 plus or minus I root 3. Right? So that's using the completion of a square to rapidly get to the solution of my auxiliary equation. In a case where it was complex, at this stage the only thing that's left over to do is to write down the general solutions. So here they are for this particular problem. So let's call this A and this one B. So A, that's got the solution y is equal to some constant A1, and I've got these two possibilities for m, so it's e, and I'm going to write it this way. Both of the solutions have a minus 3 there, so I'll take that out as a common factor. And there's my two arbitrary constants and the rest of the exponentials. Problem B here, I have a minus 3 that's common in m. And then what's left over is this plus or minus I times the square root of 3. So I could use the complex exponential form again, but I'll skip to using the sines and cosines. With the sines and cosines, I get arbitrary constant c, cosine of root 3, x plus d, arbitrary constant, sine of root 3x. And that whole thing is the argument of either the sine and the cosine. Okay. So let's now complete the discussion of this segment by launching into a case where you have an inhomogeneous term for a second order constant coefficient ODE. We will do y prime primed. Oh, I'm doing the wrong one again. Minus 4y primed plus 3y equals, let's do e to the 2x as one example, cosine of x, and e to the x as the three options for the right-hand side. So let's do those. And I'm not going to go through all of the algebra at this point. I'm just going to sketch things out. So the recipe in this particular problem follows on from the homogeneous problem. Here's the homogeneous problem, right? So step one is you solve the homogeneous problem, and in particular, the auxiliary equation for the homogeneous solutions. Having found those, I invent a trial particular solution, yp, such that a yp prime primed plus b yp primed plus cyp equals whatever's on the right-hand side. So I need to choose this thing so I get that. When I feed it into the left-hand side, that's calculating the particular solution. Having got the particular solution, I then assemble the general solution. And the general solution I get from simply adding them together. Y is yh plus yp. Remember that when you solve this, there's two possible solutions. And so there are two homogeneous solutions in there, both of which have an arbitrary constant. And having done that, if you were given some initial or boundary conditions, the fourth step would be to calculate the arbitrary constants from them. Anyway, let's go up here and proceed with the first step. So the auxiliary equation is m squared minus 4m plus 3 is equal to 0. That's m minus 3 times m minus 1 equals 0. Factorizes. So m is 3 or 1. So the solutions are e to the 3x and e to the x with suitable constants. Okay, let's now think about step 2 and go through the three options. So, in the first case, I would look at my right-hand side. So, oh, it's an exponential. Let's try an exponential. We'll feed in this constant in front to make sure it works. I take that, I plug it into there. So I get 4d e to the 2x in here, minus 4 times 2d e to the 2x, right? That's the second derivative, that's the first derivative. Now it's plus 3d e to the 2x. I need to get e to the 2x out of that. So it's clearly going to work because each term's got an e to the 2x in there. This is 4 minus 8 plus 3. Looks like d needs to be minus 1. Okay? So that's the rules, the recipe, and it worked perfectly fine in that example. Let's check out the next possible right-hand side. So now it's a cosine. When you have a cosine, a single derivative turns a cosine into a sine, which is awkward. We've got a first derivative term here, so that means that in all likelihood, for my trial particular solution, not only will I need a cosine, but I'm going to need a sine. So the next example, I'm going to try yp is equal to some constant, let's call it d1, cosine of x plus d2 sine of x. I feed them into there, do the algebra, and I should get the result. Let's do it really, really quickly. So the second derivative just introduces a minus sign. So there's a bunch of terms that I get with cosines. So in here I'm going to get minus d1. There's going to be a minus 4, and when I differentiate this once, that turns the sine into a cosine. So I'm going to get a cosine with a minus 4 d2. And then there's the plus 3 d1. So these are all of the cosine terms, and there's one on the other side. And the sine terms, I get minus d2 from the second derivative. Then there's a minus 4. Now when I differentiate this one, I get minus a sine. And then there's a plus 3 d2 equals 0. And I have to solve those for d1 and d2. That's just a little bit of algebra, etc. Okay, so far so good. Okay, so this was the first right-hand side. This is the second one. Let's have a quick look at the third one. Now, I could just press on. I try yp is some parameter e to the x. However, since I've already solved the homogeneous problem and written down the homogeneous solutions, I'm going to pause for a moment because at this stage I suddenly realize that there it is, that's a homogeneous solution. So that's not going to work. So in this particular case, the rule of principle is to just add a factor of x. So I would do that. Differentiating gives us that combo. Differentiating again gives us the following. When I take this lot and shove it into the left-hand side there, all of these x e to the x terms disappear. Right? You'll see that yp, yp primed, and yp prime prime, they all have 1 dx e to the x. So there's one of them, minus 4 of them, plus 3 of them. They all cancel. So these ones are all going to cancel, and what's left over are some e to the x terms, which happily enough give you the right-hand side once you choose d to be something. But that's algebra, so let's leave it as etc. Okay, so there it is. That's a whole bunch of examples illustrating the methods that we have developed for those 3 varieties of differential equations. And I'm now going to sign off, and we'll then do the third segment afterwards.